It's a glorious summer afternoon on July the 19th, 1989, as a United Airlines DC-10 lifts off from Denver's Stapleton International Airport bound for Chicago's O'Hare International. In less than 2 hours' time, the now crippled DC-10 will make a desperate attempt at an emergency landing in Sioux City, Iowa, with a devastating conclusion. In its final seconds airborne, the aircraft rolls to the right, its wing impacting the ground with devastating force, igniting a fireball as the wing's fuel tank ruptures. The tail section, unable to withstand the immense stresses, tears away violently, disintegrating into fragments that scatter across the airfield along with engine nacelles and sections of the fuselage that have splintered apart as it loses its structural integrity. Even as the crippled aircraft is still bouncing along the runway, emergency services spring into action. The right wing is torn off and tumbles end over end. Now barely recognisable, the main part of the aircraft, with the left wing still attached, is wrenched sideways, flipping onto its back as it slides into its final resting place upside down in a cornfield adjacent to the runways. It takes rescuers some 35 minutes to identify the debris that are the remains of the cockpit, where, miraculously, 4 pilots are still alive. Amazingly, of the 296 people aboard, 184 survived the violent crash and fire that engulfs the wreck. In its accident investigation report, the NTSB, the National Transport Safety Board, will make the assessment that, under the circumstances, the flight crew performance was highly commendable and greatly exceeded reasonable expectations. This is the story of United Airlines Flight 232. Hello everybody, I'm Phil Wilkes. Welcome aboard the Like a Pilot podcast, where we unveil the soft skills pilots utilise every time they strap into those high-speed aluminium and carbon fibre giants we call airliners. This show is your ticket to understanding the how and why behind what makes aviation one of the safest modes of travel. So, it's time to fasten your seatbelts and join me now as we embark on a journey through the skies, where pilot skills become the blueprints for high performance in any field. Since we explored the lessons of Air France 447 back in episode 9, many of you have been asking for another long-form episode. And trust me, I've been wanting to talk about United Airlines 232 for a long time. This event has fascinated me for years because it demonstrates so many of the concepts we've covered over the first year of this podcast, and many we've yet to explore. Coming out of the holiday season, I thought now would be the perfect time to bring you not only a longer episode, but also take the time to reflect back on what we've covered to date. So grab a comfy chair, sit back and relax as we explore the gripping story and the invaluable lessons of United Flight 232. I hope you enjoy listening even half as much as I've enjoyed producing it. It's a picture-perfect summer's afternoon for flying as United Airlines Flight 232 lifts off at Denver's Stapleton International Airport and makes a climbing turn towards its Chicago destination. In command of the flight is Captain Al Haynes, 57, an ex-Marine Corps flying instructor and highly experienced airline pilot with nearly 30,000 hours in the air. Over 7,000 of them on McDonnell Douglas DC-10s, the aircraft the crew is operating today. Beside him, in the right-hand seat, is First Officer Bill Records, 48. For today's sector, Bill is acting as the pilot flying. Bill is another highly experienced aviator with around 20,000 flight hours in his logbook, nearly 700 on the DC-10. Seated behind them, at his own dedicated panel, they're joined by a flight engineer. The role of the flight engineer is to control, monitor, and troubleshoot the aircraft systems, engines, fuel, hydraulics, electricals, air conditioning, and pressurization. This frees the captain and first officer to focus on flying and navigation. Flight engineers are typically recruited from the maintenance hangar floor, or are pilots in training, gaining experience before advancing to a window seat on the flight deck. The latter is the case on today's flight, with Second Officer Dudley Dvorak, 51, at the panel. While lower in seniority at United, Dudley is also a highly experienced pilot, with around 15,000 flight hours, nearly 2,000 on DC-10s. Given captains at modern low-cost carriers typically achieve their initial command between 3,000 to 6,000 hours, let's make no bones about it. This is a highly experienced crew, but that's not unusual for a legacy carrier like United. In episode 6 of Like a Pilot, on the power of incremental change, we mentioned the competencies pilots train in the simulator. These core competencies are vital in enabling a crew to operate as a highly functioning team in an emergency. Given that crew may be meeting for the first time at flight planning, possibly only an hour before departing, you can imagine the emphasis placed on the competencies of leadership, teamwork, and communication. On today's flight, however, the crew are well known to each other. In fact, they've flown together 6 times over the last 3 months. The flight deck crew is supported by 8 flight attendants in the cabin, led by Senior Flight Attendant Jan Brown. The flight progresses smoothly as the aircraft reaches its cruising level over the grain fields of Iowa, clearly visible with the blue sky clear bar a scattering of fluffy cumulus clouds. In the cabin, the 8 flight attendants are busy ensuring the safety and well-being of their 285 passengers. It's lunchtime, and they're preparing to screen a movie. Just over an hour into the journey, a loud bang reverberates through the aircraft, jolting the fuselage. The bang is so loud it's heard by people on the ground 37,000 feet below. The serenity of the cabin is replaced by vibrations and shuddering. On their instruments, the flight crew sees that the tail-mounted No. 2 engine has catastrophically failed. First Officer Bill Records turns off the airway and begins a descent to an altitude they can maintain with one of their 3 engines failed. On Captain Haynes' command, Second Officer Dvorak pulls out the checklist for severe damage to shut down the engine. Beginning the checklist, Dvorak asks Haynes to close the thrust lever for the failed engine. It's stuck. In flight simulator sessions, it always comes back. What's going on? Dvorak suggests cutting off fuel to the engines, but the fuel lever won't move. Something is binding the controls. There must be damage back there, at the tail. Almost immediately afterwards, he notices a terrifying anomaly. The gauges for all 3 of the aircraft's hydraulic systems that power the flight control systems show 0 pressure and 0 quantity. Haynes pulls down on the firewall shutoff handle, which immediately disconnects fuel, electrical and hydraulic systems associated with the engine. The autopilot disengages, and First Officer Records grabs his control yoke to take manual control. He quickly discovers that his inputs are having no effect on the flight path. "Al, I can't control the airplane." Al Haynes looks across the flight deck and sees Records' control column turned all the way to the left and pulled all the way back, yet the aircraft is moving in the opposite directions, its nose dropping as it rolls to the right. "I got it," calls Haynes, but he too finds the flight controls unresponsive to his inputs. The aircraft is now banked at an angle of 38 degrees and increasing, well beyond the 25 degrees maximum used in routine jet transport operations. Reacting swiftly and instinctively, Haynes reduces thrust on the No. 1 left wing-mounted engine to idle and firewalls the No. 3 engine on the opposite wing. The aircraft slowly begins to roll back to a wings-level attitude. We're going to leave the flight deck for a moment now. While we're gone, the crew will attempt to restore hydraulic power by deploying an air-driven generator to power the No. 1 auxiliary hydraulic pump. Spoiler alert, it doesn't help. Modern fly-by-wire aircraft don't rely on mechanical connections between the flight deck controls and the control surfaces on the wings and tail. Instead, flight control computers send signals to hydraulic actuators that move the control surfaces. The McDonnell Douglas DC-10 type first entered service in 1971. While it isn't a fly-by-wire aircraft, it also has no direct connection between its flight deck controls and control surfaces. Instead, a system of cables from the control yokes actuates hydraulic servos at the surfaces. This design is still prevalent today in aircraft such as the iconic Boeing 737. In Episode 9, during our discussion of automation lessons involving Air France 447, we explored how redundancy in flight controls guard against system failures. Applied to the DC-10, flight control redundancy begins at the primary flight control surfaces, its ailerons, elevators, and rudders all being segmented. And each surface is powered by at least two of the aircraft's three independent hydraulic systems. These systems operate separately, with their own reservoirs, pumps, and lines, routed along different parts of the airframe to minimise the risk of multiple failures due to structural damage. Power for the hydraulic systems comes from the engines, each equipped with primary and reserve engine-driven pumps. Additional backup comes from reversible motor pumps that can transfer power between systems without mixing fluid supplies. The number 3 system also has auxiliary electric pumps, ensuring basic flight control in the rare event of a triple engine failure. These pumps are powered by the air-driven generator the crew were deploying when we left them. Unlike modern aircraft, and we're going to come back to this point, but typical of aircraft of its vintage, the DC-10 was designed without any form of manual reversion or mechanical backup as a means to control the aircraft in the case of a complete hydraulic system failure. The DC-10 was designed to meet the regulations in place at the time. They required that no single failure, or even probable combination of failures, could compromise the aircraft's safety. With all of its redundancy, the odds of losing 3 hydraulic systems were calculated at 1 billion to 1. Less likely than finding a specific grain of sand on the beach. Or winning the lottery twice in a row. But there's a major problem with the odds. They assume that multiple failures must have independent causes. They don't consider black swan events. If you're unfamiliar with the term, let me catch you up. Europeans once believed all swans were white, until they arrived in Australia and discovered black swans. A black swan is a metaphor for an event considered impossible until it happens, often with catastrophic consequences. In hindsight, it might even seem obvious or predictable. Enter the black swan. The DC-10 is powered by 3 General Electric CF6 6D engines. At the front of each engine resides the fan disc. Its job is to hold the large fan blades that push air backward and generate most of the engine's thrust. Consider this. The fan blades on the engine of an A380 measure almost 3 metres in diameter. To endure the immense stresses imparted by the centrifugal forces exerted by the spinning fan blades, fan discs are crafted from advanced alloys, or, in the case of the DC-10, titanium. During the forging of the number 2 engine's fan disc, a tiny manufacturing defect was introduced, a flaw undetected during routine inspections over its 17-year service life. At 3:16 p.m. Central Daylight Time on July the 19th, 1989, as United 232 cruised at 37,000 feet, this flaw caused the fan disc to fail catastrophically. As the fan disc shattered, high-speed metal fragments hurled outwards with force exceeding the hydraulic system's protective measures. the number 2 hydraulic system was destroyed outright. Shrapnel tore through the horizontal stabilizer, severing the lines for the number 1 and number 3 hydraulic systems. In an instant, that 1 in a billion event that no one had anticipated occurred. All 3 independent hydraulic systems failed, taking with them the primary flight controls. As we left them, the crew of United 232 is currently unaware of any of this. All they know is that they've suffered an engine failure, and, for some reason, their control inputs don't seem to be working. In a student pilot's very first flying lesson, they learn about the effects of the flight controls on the aircraft's movement about 3 axes of motion. These axes intercept at right angles at the aircraft's centre of gravity. Movement about the axis that runs vertically through the centre of gravity is known as yaw and results in movement of the nose of the aircraft, left or right. Imagine viewing an aircraft from above. As the nose of the aircraft yaws left or right, the advancing wing will therefore have a greater local airspeed than the retreating wing. Due to the effect of airspeed on lift production, as well as other effects related to the swept wing design of jet airliners, the advancing wing produces more lift than the retreating wing. This additional lift on the advancing wing causes the aircraft to roll in the direction it is yawing. Yaw is usually initiated using the rudder, mounted at the trailing edge of the vertical tail section, the vertical stabilizer. But yaw is also a byproduct of a thrust differential between the engines mounted outboard of the aircraft centerline, such as the wing-mounted engines of the DC-10. In the 4th episode of Like a Pilot, using the harrowing story of the Space Shuttle Columbia disaster as a backdrop, we explored the critical role of knowledge in high-stakes environments. We examined how a strong, foundational understanding forms the bedrock of decision-making and problem-solving, empowering us with options and enhancing performance in all aspects of our life. Heady stuff. In firewalling the engine on the downgoing wing and idling the engine on the upgoing wing, Captain Haynes was able to produce enough of a yawing motion that the secondary effective roll returned the stricken aircraft to a wings level attitude. In the aftermath of the accident, at no time did Haynes ever suggest that he thought through this action. And yet, in a story that has become the exemplar of airmanship and crew resource management for generations of pilots, Haynes' instinctive reaction marks the opening move, and it all boils down to one thing: knowledge. Let's now rejoin the crew of United 232. Re-established in wings level flight, Bill Records contacts the Minneapolis Air Traffic Control Center and declares an emergency. To reduce their workload, they request the controller uses his radar to provide directions to the nearest airport. While the controller initially suggests Des Moines International, when he subsequently advises that the aircraft is headed in the direction of Sioux City, Iowa, they take up his offer of vectors to proceed to Sioux Gateway Airport. Until it's later deselected by the crew, passengers are able to listen to these interactions through their in-flight entertainment system. They're now becoming aware of the reason for the loud bang. From the flight engineers panel, Dudley Dvorak makes a PA to the cabin. "Ladies and gentlemen, we've lost our tail engine, but this aircraft can fly fine with the 2 remaining engines. We're going to descend and continue on to Chicago." In the cabin, Senior Flight Attendant Jan Brown hears a chime. On the cabin interphone, Dvorak calls her to the flight deck. When she arrives, Captain Haynes briefs her. His briefing closely following the format of the NITS tool we discussed in episode 7, Communicating with Intent. Nature of the emergency, captain's intentions, time available, and special considerations or requirements. It went something like this. "We've lost all of our hydraulics. We're having trouble controlling the plane. We're going to try an emergency landing in Sioux City in about 30 minutes. So I need you to prepare the cabin and brief the passengers. My signal when we're about to land will be brace, brace, brace. And I need all the passengers in brace position at that point. Jan, I don't know how this thing is going to turn out, so good luck. Back in the cabin, hoping to not alarm the passengers at this stage, Jan Brown composes herself in a washroom before instructing her crew to stow food service items and secure the cabin for an emergency landing. As the crew heads towards Sioux City, the Minneapolis controller hands control of United 232 to the Sioux City approach controller.
Sioux City, got an emergency for you.
That's the Minneapolis controller on the landline air traffic controllers use to transfer control between each other as aircraft depart their airspace sector.
Alright.
That's Sioux City approach controller Kevin Bachman on the other end. Minneapolis informs Bachman that United 232 has a problem and needs emergency equipment ready to spring into action at Sioux City. Bachman sees them on his radar and takes control responsibility.
I got a United aircraft coming in, lost number 2 engines, having a hard time controlling the aircraft right now. He's at a 29,000 right now and descending to Sioux City right now. He's to your VOR, but he wants the equipment standing by right now. Radar contact.
Captain Haynes establishes radio contact with Bachman on the Sioux City approach frequency.
Okay, so you know we have almost no controllability. Very little elevator and almost no aileron. We're controlling the turns by power. I don't think we can turn right, but I think we can only make left turns. Well, we're starting a little bit of a left turn right now. I mean, we can only turn right. We can't turn left.
United 232 Heavy, understand, sir. You can only make right turns?
That's affirmative.
32 Heavy, safe souls on board and fuel remaining.
We have 37.6 fuel and we're counting solar.
About a month after the accident, Haynes would later meet Bachman at the White House. Bachman tells him that he'd found his previous duty station too stressful and had transferred to Sioux City looking for something a little quieter. With Haynes' initial instinctive reaction, they know they have some semblance of control using the thrust levers, but, needing all 4 of their hands just to move the control yokes, they don't have any hands free to manipulate the thrust levers. If you're wondering what it must have sounded like on the flight deck as the crew comes to the realization that they have no direct control of the aircraft, it's around this time that the available cockpit voice recording begins.
Now the goddamn elevator's done. Very low. Elevator hard. Rudder.
Al, you want me to slow this elevator fuel backer?
Yeah, do whatever you can. Oh shit, how those doing it. Again.
If you think they sound remarkably calm, consider what Al Haynes had to say after the accident. We were too busy to be scared. You must maintain your composure in the airplane or you will die. You learn that from your first day flying. Whether the aircraft is using automation, that is, autopilot and autothrust, or it's being manually flown by the pilots, there are 2 main mechanisms by which lift production is controlled in all phases of flight. The first is power setting. Remember, as we discussed earlier, airspeed affects the amount of lift a wing produces, and airspeed is in turn affected by engine power output. Taken superficially, cruise power settings are almost set and forget. In the cruise, a jet engine is left to run for peak efficiency. This occurs at very close to its maximum continuous RPM limit, with only a small margin of additional thrust available. As any aircraft speeds along, pushing air out of its way, the air resists. This air resistance is known as drag. Just like lift, the amount of drag an aircraft produces is airspeed dependent. For any given power setting, at some point, the amount of thrust being produced is balanced by drag and the aircraft maintains a constant speed. The second mechanism for controlling the amount of lift produced is the pitch attitude of the aircraft. Elevators, attached to the tail's horizontal stabilizer, are used to pitch the nose of the aircraft up and down. This in turn affects the angle of attack of the wings, the angle at which they meet the air through which they're moving. Angle of attack directly affects the amount of lift produced. There are other factors that affect lift production, but in the cruise, apart from changing altitude and affecting air density, power and attitude are the main controls pilots have at their disposal for controlling lift production. At any given altitude, weight and airspeed, there will therefore be a combination of power setting and attitude that maintains an aircraft in level flight. Any other combination will result in the aircraft climbing or descending. It's a constant balancing act. On a large jet transport aircraft, such as the DC-10, the entire horizontal stabilizer can be moved. This allows fine adjustments to be made to the lift produced by the tail and in turn the attitude of the aircraft and overall lift production at the wings. This obviates the need for the pilots or autopilot to hold constant forces on the elevators to maintain the balance between lift and weight. But change the power and attitude combination and you need to find a new trimmed condition. Otherwise, the aircraft will go hunting for its own equilibrium at the trimmed airspeed. This is actually how the aircraft responds around its trim state at all times. But when elevator control is present, the phugoids are easily damped and not noticeable to a pilot. With the hydraulic systems lost, so too is the ability to readily affect this balance and trim the aircraft for a new power setting. While they now have the wings level, the nose of the aircraft is pitching up despite their control inputs, converting the energy of airspeed in excess of the trim state into potential energy, altitude. Due to inertia, it will overshoot the mark and soon be pitching down, this time exchanging the potential energy of altitude for an increase in airspeed. Again, it will overshoot, and this sinusoidal motion, known as a phugoid, will continue until the aircraft finds its own equilibrium for the new power setting. Any stimuli affecting airspeed, such as a gust or change in thrust, will result in a change in speed, and the process begins again. For United 232, as the flight progresses, each phugoid cycle will cost around 1,500 feet in altitude. Time for the crew to get this under control is running out. Among the first class passengers is an off-duty United Airlines captain, Denny Fitch, 46. Denny works in the training department at United and is another highly experienced operator. He has around 23,000 flying hours, nearly 3,000 on the DC-10. Jan Brown now advises Captain Haynes that a United DC-10 training check airman is on board and has volunteered his assistance. Haynes thinks he's an instructor. Maybe he'll know something we don't. Enter Denny Fitch.
My name's Al. I'm Al Haynes. Hi, Al. Denny Fitch. How you doing, Denny? Yeah, tell you what, we'll have a beer when it's all done. Well, I don't drink, but I'll sure should have one. Little right turn. Little right turn. Little right turn. All right. Now go forward. No, now come back. You gotta lead it. You gotta lead it, or it's not gonna work.
This entire conversation takes place with Fitch standing behind Haynes as he struggles with the stricken aircraft. After the accident, when Haynes goes to visit Fitch in hospital, he comes to the realization that he doesn't know what he looks like. Fitch makes a quick visual scan of the engineer's panel and quickly becomes appraised of the situation.
See what you can see back there, will you? Go back and look out the wings and see what we got. Okay.
As Denny Fitch goes back to the cabin to make a visual appraisal of the issues, the flight deck crew continues to assess what has been lost and what is available. Throughout the information gathering stage of their decision-making process, they continue to prioritise their core task, maintaining control of the aircraft.
Back on that sucker. Come on, baby. What's the hydraulic quantity? Oh, 0. All over? All over. Quality's gone, huh? Yeah, all quality's gone.
Haynes makes a comment to the crew. "We're not going to make the runway, fellas." Despite this assessment, the crew continues to work towards a solution. A common saying in aviation circles is that you should continue to fly the aircraft to the scene of the accident. It says a lot, not only about prioritization, but also focusing on what you can control. Prioritizing performance over results is definitely something we need to come back to in a future episode. There's a knock on the door as Denny Fitch returns from the cabin.
Unlock that fucking door. Unlock it. Pull back.
Fitch and Haynes move to the review stage of the decision-making process, sharing what they now know.
Awesome. We have no hydraulic fluid. That's part of our main problem. Both your inboard ailerons are sticking up. That's more than I can tell. I don't know that's enough. Well, that's because we're turning maximum turn. Yeah. So I'm steering the airplane. Okay, okay. Sorry, go ahead, help. Just don't worry about it. Yell what you want, I'll help you. Right, close one, put two up. What we need is some elevator control, and I don't know how to get it.
Haynes delegates control of the thrust levers to Fitch. Until now, with the number 2 thrust lever frozen, it was impossible for Haynes or Records to hold both of the usable thrust levers at once. While now reasonably sure that their inputs are not affecting control of the aircraft, Haynes and Records continue to attempt to control their aircraft with their yokes. Haynes would later say, "Had we known what we know now, I don't know if we would have let go of the yoke even now. To let go of the yoke completely is extremely difficult to do. After almost 40 years of flying airplanes and holding onto something, not having something to hold onto, I don't know if we could do that." At stages, they think they have the elevators under control, but in reality, they have no control. Fitch is now solely controlling the aircraft using thrust alone. He finds that by moving the thrust levers asymmetrically, he has a semblance of directional control. He also finds that he is roughly able to control altitude, damping the phugoid motions by working against them. As the aircraft reaches the apex of each phugoid and starts down, he adds power to help the speed build up and create extra lift to get the nose pitching back up again. Harder is closing the thrust levers and reducing power as the nose starts pitching up, cognizant that as the aircraft slows, it approaches its stall speed, another concept discussed in our automation episode. All the while, the crew call commands to "Give us a right bank, bring the wing up, that's too much bank, try to stop the altitude." Captain Haynes radios Sioux City approach, keeping all parties informed and continuing to gather information for the option generation phase of his decision-making process.
We have no hydraulic fluid, which means we have no elevator control, almost none, and very little aileron control. I have serious doubts about making the airport. Have you got someplace near there that we might be able to ditch? Unless we get control of this airplane, we're going to put it down wherever it happens to be.
United 232 Heavy, roger, standby 1.
Fitch comments that they need to get this thing down. We're in trouble. A great leader knows that they don't have to have all the answers. When time allows, great leaders will involve their team in planning, and as we discussed in episode 2, there is almost always time for at least a rudimentary decision-making process. Until now, Haynes has been open about not having all the answers and has used all resources available to him, creating the environment in which the decision-making process has involved his crew and external agencies. But great leaders are also competent communicators, knowing what, how, where, when, how much, and with whom they need to communicate. In other words, their approach to decision-making and communicating is flexible, dictated by circumstance. Having made the decision to continue to Sioux City and attempt a landing, we see a shift from a collaborative to a more directive style of communication. Haynes begins to delegate. As the leading edge slats and trailing edge flaps are also hydraulically actuated, he instructs Second Officer Dvorak to start gathering information on making an approach to land without these high lift devices available to slow the aircraft. Once again, prioritising flight path assurance above all else, he looks for ways to manage his workload. While all the necessary information is possibly available to him on flight deck charts, he asks the controller for details of the Sioux City airport. Kevin Bachman provides the frequency for the landing guidance system for runway 31, the runway in use, and advises Haynes that it's 9,000 feet long, ample for a DC-10 making a normal approach to land. Haynes orders Dvorak to start dumping fuel to lighten the aircraft for landing and reduce the runway length required. While Haynes continues to provide guidance to Denny Fitch behind the thrust levers, information flows forward from Dvorak. He's calculated that the minimum speed without slats or flaps will be 200 knots, 40% faster than their typical approach speed. They'll be attempting to land at 230 miles or 370 kilometers per hour. That's a lot of excess energy that they will need to dissipate, and they have no brakes. Earlier, when Denny Fitch returned from his inspection of the control surfaces, he'd mentioned that the flight attendants were slowly preparing the cabin for landing. At the time, Haynes had commented, "They better hurry, we're going to have to ditch, I think." He now calls Jan Brown back to the flight deck to ensure the cabin will be ready, and gives her his final instructions.
We have almost no control there. We have no hydraulics at all. We're going to go to Sioux City. And we're going to try and put it into Sioux City, Iowa.
Yeah.
It's going to be tough. It's going to be rough.
So we're going to evacuate the shore.
We are. Well, we're going to have the gear down.
Yeah.
And if we can keep the airplane on the ground and it stops standing up, give us a second or two before you evacuate.
What's going to be the
We're down 1,500. Roll back over for brace.
signal?
The brace will be the signal. It'll be over the PA system. Brace, brace, brace. And then if we have to evacuate, you'll get the command signal to evacuate, but I really have my doubts we'll be standing up, buddy. Good luck, sweetheart.
Did you pick up Haynes mentioning the landing gear? The landing gear is another hydraulic system, but there are options available to get it down when the normal lowering mechanism is inoperative. A robust decision-making process considers options, and the crew have been through this process earlier. Given the rates of descent they were seeing on the flight deck, the one thing the crew has all agreed upon was that they wanted the landing gear down to act as a shock absorber. But which of the two methods available to them would they use? When hydraulic pressure was lost, the gear would have fallen down slightly and would be currently resting on the landing gear doors. Putting the landing gear handle in the down position would mechanically unlock the landing gear doors, and they could then rely on gravity to let the gear fall into place and lock down. But an alternative system is available using a lever in the flight deck floor. For roll control, there are 4 ailerons on the DC-10. At high speed, the inboard ailerons are used. The outboard ailerons remain locked in a neutral position until they are unlocked for landing when the flaps are lowered. They are also unlocked when the alternate method for gear extension is used. The crew extend the landing gear via the alternate method. They hope that as the outboard ailerons unlock, there may be some trapped hydraulic fluid, and they will regain some semblance of roll control. The gear locks down, but they still have no direct roll control. Sioux City continues to work with the crew as they manoeuvre into position for an approach to the airport. There's a constant communication flow, so everyone is appraised of the situation. As a result, options continue to be generated and decisions re-evaluated.
232 Heavy, do you think you'll be able to hold about a 240 heading?
Yeah, we're trying to turn to it right now.
Roger. When you get turned to that 240 heading, sir, the airport will be about 12 o'clock at 38 miles.
Okay, we're trying to control it just by power alone now. We have no hydraulics at all, so we're doing our best here.
Roger, and we've notified the equipment out in that area too, sir. The equipment's here on the airport standing by, and they're sending some out to that area.
We're going to have to continue one more right turn. We've got the elevators pretty much under control within 300 or 400 feet, but we still can't do much of this terrain.
United 232 Heavy, Roger. I understand you do have the elevators possibly under control. We've got to hold altitude.
Negative. We don't have it. We are better, that's all.
Roger. United 232 Heavy, there's a small airport at 12 o'clock and 7 miles. The runway's 4,000 feet long there.
Hey, I'm controlling it myself right now. As soon as the captain gets back on, he'll give me a hand here. He's talking on PA.
Roger.
Okay, United 232, we're starting a left turn back to the airport. Since we have no hydraulics, braking is going to really be a problem. I would suggest the equipment be towards the far end of the runway. And I think under the circumstances, regardless of the condition of the airplane when we stop, we're going to evacuate. So you might notify the ground crew equipment that we're going to do that.
United 232 Heavy, Wilkes, sir, and if you can continue that left turn to about a 220 heading, sir, that'll take you right to the airport.
With the fuel load now reduced as much as practical and the gear down, the captain directs flight crew to lock their shoulder harnesses and put everything away.
Lock up and put everything away. There goes the slats.
The approach controller now requests final adjustments to the aircraft track to align for landing on runway 31, the most into-wind runway.
United 232 Heavy, you're going to have to widen out just slightly to your left, sir, to make the turn to final, and also that'll take you away from the city.
Whatever you do, keep us away from the city.
United 232 Heavy, been advised there is a 4-lane highway up in that area, sir, if you can pick that up.
Okay, we'll see what we can do here. We've already put the gear down, and we're going to have to be putting on something solid if we can.
United 232 Heavy, Roger. The airport's currently at your 1 o'clock position, 10 miles. And United 232 Heavy, if you can't make the airport, sir, there is an interstate that runs north to south to the east side of the airport. It's a 4-lane interstate.
We're just passing it right now. We're going to crash the airport.
United 232 Heavy, Roger. And advise when you get the airport in sight.
Got the runway in sight. We'll be with you very shortly. Thanks a lot for your help.
Haynes instructs Dvorak to make a PA, giving a 2-minute to land warning.
United 232 Heavy, the wind's currently 360 at 11, 360 at 11. You're cleared to land on any runway.
You want to be particular and make it a runway, huh?
Captain Haynes is quite the comedian.
010 at 11, and there is a runway that's closed, sir, that could probably work too. The south, it runs northeast to southwest.
Pretty well lined up on this one, or I think we will be.
All right.
On his radar, Kevin Bachman sees the aircraft is actually lined up on the decommissioned runway 11.
United 232 Heavy, Roger, sir. Yeah, that's a closed runway. That'll work, sir. We're getting the equipment off the runway, and they'll line up for that one.
How long is it?
At the end of the runway, it's just a wide open field, so the length won't be a problem.
Okay.
Within 2 short minutes, the airport emergency services have repositioned from runway 31. The crew's attention is now almost completely directed to manipulating the throttles. Referencing the first officer's instruments, Denny Fitch believes that he has the aircraft lined up and on a normal glide path to the field. With around 30 seconds remaining airborne, the PA is used again to deliver the brace command to the cabin. Brace, brace, brace. Normally, the aircraft would approach at around 140 knots, descending between 700 and 800 feet per minute. 8 seconds before touchdown, the airspeed is 215 knots and the sink rate exceeds 1600 feet per minute. The aircraft's ground proximity warning systems start issuing continuous sink rate warnings to the crew. There isn't much they can do about it. Denny Fitch is doing a great job behind the thrust levers, smoothly controlling the oscillations in pitch and roll. They have the aircraft aligned with runway 11 and they are on a trajectory to touch down in the landing zone. Unfortunately, they're about to run out of luck. A mere 100 feet above the ground, the aircraft starts the down cycle of another fugoid, and the right wing drops rapidly. Haynes issues instructions for a correction. Fitch desperately tries to level the wings, but the engines don't respond in time.
Let's turn left. Help me turn left so we know what it's doing. Back. Let's start down. We have to ease it down. We gotta ease it down now.
Don't pull the spoilers on the touch.
Down the brakes with me. Left turn. And close the throttle. Close them all. Left turn, close the throttle.
No, I can't pull them off if you'll lose it. That's what's turning you.
Okay, all right.
Okay.
Back out. Left throttle. Left.
After 44 harrowing minutes, the DC-10 crashes onto the runway with a descent rate over 6 times higher than normal. The impact claims the lives of 112 people, including one flight attendant. Tragically, some passengers survived the initial crash, but succumb to smoke inhalation, primarily in a section where the ceiling collapsed. Despite this devastation, 184 people survive, a testament to the time the crew had to prepare the cabin for impact. One of the critical factors, according to the NTSB, was that passengers were briefed on bracing for impact. The brace position, which flight attendants emphasised during pre-flight safety briefings, undoubtedly saved lives that day. So, the next time you hear that safety demonstration, consider this. Those instructions could be the difference between survival and tragedy. Pay attention to the brace position. Keep your seatbelt fastened until the aircraft stops. And don't overload the overhead bins. It's all designed to increase your odds if something goes wrong. Landing a plane under normal conditions requires precision. Touching down at around 140 knots within 1,500 feet of the runway's threshold and perfectly aligned with the centerline. United 232 faced an almost unimaginable challenge. A 215-knot approach speed and descent rates 6 times faster than normal, all with no direct control over flight surfaces. Despite this, the crew managed to touch down within the normal zone of the runway, 1,600 feet from the threshold, albeit slightly left of centerline. This would be a remarkable feat for a fully functioning aircraft. Given that the crew at times didn't think they would even make a runway, this is astonishing. Maybe it's easier than it sounds. Could pilots be trained for this type of eventuality? The NTSB conducted simulations to evaluate the crew's performance, assigning experienced DC-10 pilots, check airmen, and even McDonnell Douglas test pilots to replicate the scenario. Almost none made it to the runway, let alone executed a survivable landing. Deeming it impossible to design a simulator exercise to train for the eventuality facing the crew of United 232, instead they published generalised advice, recommended hydraulic system enhancements, and encouraged the development of backup flight control systems. Early in the episode, I said I'd return to manual reversion and mechanical backup. Let's just close this out by confirming that newly certified wide-body aircraft are designed with alternative sources of motive power separate from those sources for their normal control systems. The NTSB concluded that what the crew of United 232 achieved exceeded all reasonable expectations and demonstrated unprecedented skill, ingenuity, and teamwork. The tragic outcome of Japan Airlines Flight 123 offers a sobering contrast. In 1985, this Boeing 747's aft pressure bulkhead ruptured, disabling all 4 hydraulic systems and tearing off the vertical stabilizer. The pilots fought heroically using differential thrust for over 30 minutes, but were unable to keep the aircraft under control. Japan Airlines Flight 123 crashed into mountainous terrain, claiming 520 lives in what remains the deadliest single aircraft accident in history. Unlike JAL 123, United 232's crew had some critical advantages: the stabilising influence of a mostly intact airframe and flat terrain. But their survival is also a testament to preparation, skill, and their refusal to give up. Throughout this episode, I've taken you through the extraordinary events of United Flight 232, and I hope it's given you a better sense of just how remarkable the outcome really was. But beyond the awe-inspiring airmanship and the survival of so many, there are lessons we can all take away from what happened that day, regardless of the field we work in. So let's explore some key takeaways from this story that might just change the way you approach leadership, teamwork, and problem solving. The first lesson I want to highlight is that leadership isn't about having all the answers. It's about using all the resources available to you. In a 1991 lecture at NASA's Ames Research Center, Al Haynes emphasized this when he said, "We had 103 years of flying experience up there in the cockpit trying to get that airplane on the ground. Not 1 minute of which we had actually practiced, any one of us. So why would I know more about getting that airplane on the ground under those conditions than the other three?" This speaks volumes about the importance of teamwork and trusting your colleagues. A great leader recognizes their own strengths and weaknesses, and rather than working in isolation, they draw upon the expertise of their team. This is exactly what Haynes did. He recognized that the combined knowledge of his crew, rather than just his own, would get them through this seemingly impossible situation. In a similar vein, there's a well-known anecdote about Henry Ford, who, when questioned during a court case about his company's operations, pointed out that he didn't need to know every minute detail about engineering or manufacturing. Why? Because at the press of a button, he could summon someone with the right expertise. Ford's point here is simple. Leadership is about recognizing when to delegate and creating an environment where everyone can contribute their knowledge for the greater good. Haynes did exactly that, and the outcome of United Flight 232 speaks to how valuable it is to let the team's collective intelligence shine. Communication is the glue that holds all of this together. Haynes and his crew exemplified how open and constant communication can keep a team aligned under pressure. Communication isn't just about giving orders, it's about ensuring that everyone feels heard and knows what's happening at every step. Haynes himself said, "If we'd not let everybody put their input in, it's a cinch we wouldn't have made it." He understood that their survival was not only dependent on their skills as pilots, but on their ability to communicate openly with each other and with air traffic control and with maintenance experts. This same principle applies to any team, whether it's a flight deck, a boardroom, or even a sports team. When you bring everyone into the conversation, you ensure that all perspectives are considered and more solutions become available. This was clearly demonstrated when Second Officer Dvorak spent 33 minutes communicating with United's maintenance team and other agencies. Unfortunately, they weren't able to offer much in the way of solutions. There were no procedures in place for their unique situation. But the decision to involve others, even just to cross-check their thought processes or prepare resources on the ground for their arrival in Sioux City, were another layer in making the seemingly impossible possible. Finally, one of the most important lessons from United 232 is the value of continuing to work towards a solution, even when the end goal feels uncertain. As Captain Haynes reflected, there were times when all 4 of us had serious doubts as to making the airport, but we knew in the back of our mind that where we were, if we had to ditch, we could probably find some fairly flat land, and we might have a chance of survival. So that relieved a lot of the pressure on us. They didn't give up. They kept working the problem, adjusting their approach as necessary. In life, whether you're preparing for a big exam, playing a high-stakes game, or facing any difficult situation, focusing on the task at hand and staying adaptable is often the key to turning things around. The crew of United 232 demonstrated that when you persist, work together, and focus on what's within your control, even the most daunting challenges become surmountable. To summarise, what makes United Flight 232 stand out isn't just the incredible skill of the pilots, it's the remarkable teamwork, the seamless communication, and the determination to keep pushing towards a solution, no matter how dire the circumstances. The crew of United 232 managed to land an aircraft with no functioning hydraulics or flight controls, something that many experienced pilots couldn't even simulate. As the Aircraft Owners and Pilot Association put it when Captain Haynes passed in 2019.
It's one of the greatest feats of airmanship and crew resource management of all time.
For me, these are the lessons that high-functioning leaders and teams can take away from United 232. Don't work in a silo. Use all resources available to you. Communicate openly. And most importantly, never stop working towards the solution. We'll leave this episode now in the hands of Captain Haynes, reflecting soon after the accident.
There is no hero. There is just a group of 4 people who did their job, and it was an unusual circumstance, but we put our best resources and knowledge together and did what we thought was best.
Until next time, thank you for listening to the Like a Pilot podcast. If you've liked the show, please remember to subscribe and don't forget to tell your friends. For more information, check out the show notes at philwilkes.com/podcast, where you'll find links to the NTSB report and Captain Haynes' NASA lecture. If you'd like to support the Like a Pilot podcast, our Patreon page is available at patreon.com/likeapilot. The Like a Pilot podcast, as always, is written and produced by me, Phil Wilkes.